Hello, my dear students. In this lecture, we are going to see one question on convection. This is the best design question on the convection. Now, here in this question, the first four or 3 to 4 questions are on convection, that is heat transfer subject, and last 2 questions are on fluid mechanics. So these questions also we will solve here. So let us understand the question. The question is, water flows through a 20 mm ID at a rate of 0.01 kg per second. Now here, and entering at 10 degrees Celsius. Now here, water is flowing through a ID means inner diameter. Therefore, it is flowing through a pipe. So let us draw the pipe. Right. Let us say this is the pipe. Right. And through this pipe, the water is flowing. The pipe of length L. Let us say this is the pipe of length L. Right. And diameter D. For this pipe, diameter is given D, which is nothing but diameter is given 20 mm inner diameter, which is nothing but 20 into 10 to the power minus 3 meter. This will be the diameter, right? And through this pipe, the water is flowing. Inside this, there is a water which is flowing, right? Let us say, so here water is flowing. This is the water, and here they have again mentioned the mass flow rate of water is 0.01 kg per second. So m dot is nothing but 0.01 kg per second. Then entering at 10 degrees Celsius. Therefore, this water inlet temperature, here this water temperature at inlet, that is T infinity, surrounding fluid temperature at inlet is 10 degrees Celsius, right? At this center line, right? Here always the temperature is given on center line, right? Here also there will be a circular shape. Now here, then the tube is wrapped from outside by an electric heating element that provides a uniform flux of 15 kilowatt per meter square. Now this tube is wrapped around with the help of electric heating element, and because of this, on this tube, the uniform heat flux is produced. This heat flux on this tube, the uniform heat flux Q is produced. Right. This will be the uniform heat flux Q. Right. Therefore, this Q is given, uniform heat flux Q is given 15 kilowatt per meter square, which is nothing but 15000 watt per meter square, 15,000 watt per meter square, right? Then, if the exit temperature of water is 40 degrees Celsius, now here at the center line for this tube, at the center line, the exit temperature of water, that is T infinity O, is 40 degrees Celsius, right? T infinity O will be 40 degrees Celsius. Estimate. Now here, one by one, let us say the questions. Question number 1, very first question, that is A, is Reynolds number. Here we have to find Reynolds number. Re is equal to question mark. Question number 2. Question number 2 is the heat transfer coefficient, that is H, convective heat transfer coefficient. This water will be having some convective heat transfer coefficient H, that we have to find. H is equal to question mark. Number C, right, is the length of pipe needed. Here this length of pipe we have to find. L is equal to question mark. Then D is the inner tube surface temperature at exit. Now here they are asking what is the tube temperature, that is wall temperature at exit, right? Let us say the wall temperature at exit is T wall, somewhere here. T wall at exit, that is at outlet. T wall at outlet. This we have to find, right? Therefore D is surface wall temperature at outlet, right? Then D, after D is the friction factor. This is from fluid mechanics. Is friction factor, F, small f. Then the pressure drop in the tube. This is again from fluid mechanics. That is, next question is pressure drop in the tube, del P. Right. Then G is the pumping power required if the pump efficiency is 60%. Again, this is from fluid mechanics. It is pumping power. Right. Pump power. Pump power is equal to question mark. Right. If pump efficiency is 60%. If efficiency of pump, let us say here pumping power I will represent with P, right? Here pumping power I will represent with P, right? Question mark. If efficiency of pump is 60%, right? Then neglect the entrance effects. Properties of water at mean temperature of 25 degrees Celsius are. Now here density of water is given, specific heat of water is given. Here let us check the unit. Newton second per meter square is a unit of dynamic viscosity. Therefore, this is the dynamic viscosity, and K is the thermal conductivity. Therefore, here the properties are given. We can say density of water is given 997 kg per meter cube. In the last line, here all the values are written. Then specific heat of water, Cp of water is given 4180 joule per kg Kelvin. Then dynamic viscosity, which is written here m, but it is actually dynamic viscosity, that is Newton second per meter square is the unit of dynamic viscosity, which is nothing but 910 into 10 to the power minus 6 Newton second per meter square. Then thermal conductivity is given K, which is nothing but 0.608 watt per meter Kelvin, right? And we have to find these all values. So let us find one by one. Now here, let us find them one by one. First of all, we will calculate Reynolds number, right? So very first is Reynolds number, A, Reynolds number. Now my dear students, for this flow through pipe, the Reynolds number is here rho VD upon mu. This is the formula to find Reynolds number. Here density is given, density of water is given, velocity of water is unknown. So we have to calculate velocity of water. Diameter of water is known as well as the viscosity is known. But here velocity is unknown. So before calculating Reynolds number, first we have to calculate velocity of water. Right. So let us find velocity. Now here mass flow rate is given. Now my dear students, can I say at inlet through this circular area, the mass flow rate is 0.01 kg per second. Per second, 0.01 kg mass of water is entering into the tube. Therefore, this mass flow rate from the fluid mechanics or from the thermodynamics is nothing but rho AV, where rho is density, A is the area through which it is flowing, and V is the velocity. Therefore, this mass flow rate will be equal to rho into area is pi by 4d square, because it is flowing through this diameter or not, right? It is flowing through this diametric area, right? Therefore, into velocity V, into velocity V. So let us find this velocity. Velocity will be 4m dot. You have a rho pi d square, which is nothing but 4 into m dot is given 0.01. You have a rho density is 997 into pi into diameter is 20 into 10 to the power minus 3 whole square, right? So if I calculate here velocity, then this velocity of flow I will get 0.032 meter per second, right? This will be the velocity of flow. A very important parameter. Also for next questions, this velocity is required. So here I will write the velocity of flow will be equal to 0.032 meter per second, right? Now once the velocity is calculated, let us find this Reynolds number. Therefore this Reynolds number will be equal to density is nothing but 997, velocity just we have calculated, diameter is given, right? And viscosity is also given. So let us put the values. Therefore it is 997 into velocity is 0.032 into diameter is 20 into 10 to the power minus 3 divided by viscosity is 910 into 10 to the power minus 6. Therefore here the Reynolds number of this flow will be equal to, let us find this Reynolds number. So I will get Reynolds number is equal to 700, right? Therefore this is the answer for first question. What is the Reynolds number? Reynolds number is 700. Now my dear students, it is a flow through pipe, and whenever for flow through pipe, whenever this Reynolds number is less than 2000 or equal to 2000, it is called laminar flow. And as 700 is less than 2000, therefore the type of flow is laminar flow. So here we have to use the formulas of laminar flow. Therefore here I will write Reynolds number value. Reynolds number is 700, right? So let us use the formulas of laminar flow and flow through pipe. Now to solve second question, that is convective transfer coefficient EH, we need Nusselt number, because we know that the Nusselt number is nothing but HL divided by K, where L is nothing but characteristic dimension. For flow through pipe, characteristic dimension is nothing but diameter of pipe. So instead of L, write here diameter, because here for length we have length is a L is a length. So don't write here L, otherwise you will get confused, right? If I write here D, then it is absolutely fine. This D or whatever may be the writing you here, this is a characteristic dimension. For flow through pipe, it is a diameter, right? It is HT divided by K. So if I want to calculate EH, I have to calculate Nusselt number. Therefore EH will be equal to Nusselt number into thermal conductivity divided by diameter, right? So first of all, I have to calculate Nusselt number. Now here we have specified the, or we have stated what is the case it is. It is a laminar flow. It is a laminar flow, again through pipe, very important. laminar flow through pipe. Now for laminar flow through pipe, we have two values of Nusselt number. One is for constant wall temperature, other one is for constant heat flux. And here they have mentioned uniform flux, that is constant heat flux. They have given constant heat flux. Therefore, laminar flow through pipe for constant heat flux, for constant or uniform heat flux, the Nusselt number value we have seen, right, that Nusselt number is nothing but 4.364. This is the value of Nusselt number. So my dear students, and for constant wall temperature it is 3.66. But here they have mentioned uniform flux, that is constant heat flux. Therefore, I have to use value 4.364. So let us put this value. Thermal conductivity is given, diameter is also given. So you will get EH value. Therefore, this convective heat transfer coefficient EH will be equal to Nusselt number is 4.364 into thermal conductivity is nothing but 0.608, but diameter is 20 into 10 to the power minus 3. So let us solve here for EH. Then this EH value you will find 132.5, which is watt per meter square Kelvin. Right. This will be the convective heat transfer coefficient for this water. Right. So again this EH is required. This EH is second question. This EH is required later. So let us write here. So here we have calculated EH as 132.5 watt per meter square Kelvin. Right. Now let us go for third question. Now as the water is flowing through this pipe and during flow the temperature of water is increasing, right? And here the uniform heat flux is provided. Because of this uniform heat flux, the temperature of water is increasing. Therefore, the heat transfer rate for steady state condition, this heat transfer rate will be equal to uniform heat flux into area, that is watt per meter square into meter square will become watt. Therefore, uniform heat flux into area is equal to. Now for temperature change of water, it is mCp dt of water. Therefore, it is mCp dt of water, that is T infinity O minus T infinity I. Change in temperature of water is from T infinity O to T infinity I, that is from 10 degrees Celsius to 40 degrees Celsius. Therefore, I have to consider final temperature minus initial temperature. Right. So from this we will get the length. From this we will get the length, because in area there will be a length. Right. Length of this pipe we have to calculate. Therefore, here this heat flux into area. Now, on which area the heat flux is applied? Now, my dear students, for this mass flow rate, we have considered this cross-sectional area for this mass flow rate. That is m dot is equal to rho AV. In this formula, the area is cross-sectional. But here, this heat flux is applied on surface area. Therefore, this area is a surface area. Therefore, it will become pi dl. Pi d into L is equal to mCp T infinity O minus T infinity I. So let's put the values. Q is 15,000 into pi, diameter is 20 into 10 to the power minus 3 into length is equal to mass flow rate is 0.01, right? Is equal to 0.01. Cp is also given 4180 into 4180 into temperature difference is 4T minus 10. Right. Now, my dear students, again in this complete equation, only here length of pipe is unknown. So let us solve this equation for length of pipe. And if I calculate, I will get length of pipe as 1.33 meter. Right. This will be the length of pipe. And this is your third question. So this question again, this answer is again later required. So let us write length of pipe is 1.33 meter. Now, my dear students, the fourth question is to find the wall temperature, that is surface temperature at exit, this T wall at outlet. Now, my dear students, on this surface, that is on this cylindrical surface, the uniform heat flux of magnitude Q is applied. Because of this Q, the surface gets heated and the temperature of this surface becomes T wall. Right. And my dear students, between this wall temperature and this fluid temperature, can I say between them there will be a convection? Definitely. Between here, are you able to visualize this? Between this wall temperature and between this fluid temperature, between them there will be a convection. Definitely there will be a convection heat transfer, right? Therefore, this heat flux at each and every location is same. Therefore, this heat flux is nothing but the convection heat transfer is nothing but HA T wall minus T infinity is the convection heat transfer. Wall temperature minus surrounding fluid temperature. Now this heat flux is uniform. Therefore, we can say Q by A, which is nothing but heat flux, is equal to EH, convective transfer coefficient EH into T wall minus T infinity. Now, if I want to calculate this wall temperature at outlet, then I have to consider this fluid temperature at outlet. If I want to calculate this wall temperature at inlet, I have to consider this fluid temperature at inlet. But here they are asking at outlet, therefore let us use these outlet conditions. Therefore, this heat flux will be equal to EH into T wall at outlet minus T infinity at outlet. So this is given 15,000 is equal to EH we have calculated 132.5. It is 132.5 into T wall at outlet we have to calculate, and T infinity surrounding fluid temperature at outlet is 40 degrees Celsius. Right. So my dear students, again in this equation only T wall at outlet is unknown. So let us solve for outlet wall temperature, and I will get 153. I will get answer as 153.2 degrees Celsius. 153.2 degrees Celsius. And this will be the outlet wall temperature, surface wall temperature. Right. Now, my dear students, up to this, there is a heat transfer. And after that, this E, F, and G, this is purely fluid mechanics. Now, here to solve these questions, you must know the concepts of fluid mechanics and formulas of fluid mechanics. Here we will solve the question, but if anybody don't know these formulas, then it is absolutely fine. After watching fluid mechanics lectures or after in fluid mechanics also such type of questions you are going to solve. Don't worry about that. So here for this question, let us solve these questions also. Now the E question is friction factor. And my dear students, very simple formula, simple relation of friction factor with Reynolds number from the fluid mechanics is this E is friction factor. This friction factor is nothing but 64 divided by Reynolds number. Right? Whenever it is a flow through pipe and laminar flow, then it is 64 divided by Reynolds number. So let us write down 64 divided by Reynolds number we have calculated as 700. Right here you will see on the right side we have written the values. Therefore divided by 700. So this friction factor we will get is equal to 0.0915. Right, this will be the friction factor. Now next question is to find this pressure difference. It is pressure drop. F is pressure drop in pressure. Now my dear students, drop in pressure is nothing but rho gh. Right, it is rho gh. Rho is density. It is given. G is acceleration due to gravity. We know that 9.81. H is a drop in head. Drop in pressure, drop in head. Right. Whenever it is a drop in pressure, then it is a drop in head. And this drop in head loss due to friction, HF, or we can say HF. Del P is equal to drop in pressure is equal to rho G HF. This head loss due to friction from fluid mechanics, the formula is, it is will be equal to F L V square divided by 2 GD. This is a formula to find head loss due to friction for flow through pipe, where F is a friction factor, just we have calculated. L is a length of pipe, V is a here velocity, we have calculated here, length also calculated, velocity also calculated. G is acceleration due to gravity, D is a diameter of pipe. So let us put here, therefore this pressure drop del P will be equal to rho G into F L V square divided by twice G D. Therefore here can I say, here this G will get cancelled, right, and the formula will become, it is equal to rho G is get cancelled, rho FL V square divided by 2D. So let us use this formula to find this pressure drop. Therefore this pressure drop will be equal to here rho FL V square divided by 2D, sorry, here 2D. So let us put the values. Density is given 997. Friction factor, just we have calculated the friction factor, which is 0.0915 into length. Right here, length also calculated, which is nothing but 1.33. The length we have calculated as 1.33. Then this velocity also calculated 0.032 square. Therefore, it becomes 0.032 square whole divided by 2 into diameter. Diameter is nothing but 20 into 10 to the power minus 3. From this, you will get this pressure drop. So let us calculate this pressure drop. You will find 3.1 Pascal. That is 3.1 Newton per meter square. This will be your pressure drop. The last question is to find pumping power required if pump efficiency is 60%. Now, my dear students, from the fluid mechanics, that is turbomachinery topic, I am going to directly use here formula. Now, if you don't know this formula, then it is absolutely fine. In turbomachinery, you are going to learn this formula. Right. Now, here, efficiency of pump, which is 60%. This efficiency of pump is nothing but here m dot into del p by rho whole divided by this power required, pumping power required for the pumping. This is the efficiency of pumping. Therefore, we can say the power required, pumping power required will be equal to m dot del p divided by rho into efficiency of pump. Right. So let us put the values. M dot is mass flow rate 0.01 into pressure drop, just we have calculated 3.1 divided by density is given 997 into efficiency of pump is 60%, which is nothing but 0.6. 60% means it is 0.6. Right. Now with the help of this formula, let us find this power required. Therefore, I will get power required will be equal to 5.18 into 10 to the power minus 5 watt. This will be pumping power required. Right. Thank you, dear students. In next lecture, we will see one more numerical on this topic.